Here we look at shapes of molecules which do include lone pairs, and we're going to see that the inclusion of a lone pair will distort the basic shape. It is very, very important that when we're looking at molecules with lone pairs that we know the 5 basic shapes and their bond angles. So we're going to start by looking at a molecule where we've got 3 pairs of electrons and where we've got 2 bonding pairs and 1 lone pair. Now this is obviously based on a trigonal planar structure, which has 3 bonding pairs with bond angles of 120 degrees. Now it's actually this particular molecule where you've got 2 bonding pairs and a lone pair is actually very rare. It's very unusual. But an example would be this here. And this molecule looks very strange, especially if you've done some organic chemistry, but you've got to kind of trust me that this actually does exist. It's called a methylene molecule. And what we've got here is we've got a CH2, but instead of one of these bonds here being a bonding pair of electrons, I'm going to replace this now with a lone pair, which I'm going to show like this. Now, if this bond here was a bonding pair, not a lone pair, the bond angle here between these 2 bonding pair of electrons would be 120 degrees. But because bonding pair, lone pair repulsion is greater than bonding pair repulsion, it pushes these bonding pairs close together. What it's saying is that these bonding pairs are going to try and get far apart from this compared to if it was a bonding pair, and it pushes these bonding pairs closer. And that reduces the bond angle, and that means it's going to be less than 120 degrees. Remember, if this was a bonding pair, it would be 120 degrees. Bonding pair, lone pair repulsion is greater, forces these bonding pairs close together. The actual bond angle is actually quite a bit less than 120 degrees, but I think if you said something like 115, something like that, you would probably be okay. They would give you quite a wide range in what the shape of the molecule was. You've just basically got to realise that it's less than 120 degrees. The name of the shape is based on the shapes formed by the bonding pair. So looking at the shape based on this molecule here, and that would be bent. We call that a bent shape. Now, what we're going to do in each of these examples, that this number in effect is going to go up each time. And we're going to look at the various permutations with these pairs of electrons. Now, we've looked at 3 pairs. There are only 2 permutations there, 3 bonding pairs, no lone pairs. And we've now looked at the other permutation now of 2 bonding pairs and 1 lone pair. So now we're going to have a look at where we've got 4 pairs of electrons around a central atom. And remember that this now is based on a tetrahedral. Now, if it had 4 bonding pairs of electrons, it would be a tetrahedral with a bond angle of 109.5. But what we're going to do now is replace one of those bonding pairs with a lone pair. And an example here would be ammonia. Ammonia is a molecule which contains 3 bonding pairs and a lone pair. Now, again, because bonding pair, lone pair repulsion is greater than bonding pair, it pushes these bonding pairs of electrons a little bit close together, and as such will reduce the bond angle. We do need to know the exact bond angle in this particular example, and that is 107 degrees. So we can explain that because this is something you might be asked to explain. So, as lone pair bonding pair repulsion is greater than bonding pair repulsion, the bond angle is reduced from 109.5 degrees to 107 degrees. So what we're saying is that if this was a bonding pair, this bond angle would be 109. But because of this inclusion of the lone pair, because the repulsion between this lone pair and this bonding pair is greater than the repulsion between these two, it forces these bonding pairs close together and reduces the bond angle between the bonding pairs. Now, the name of this molecule is something that you do need to be aware of, and it's called a trigonal pyramidal. Sometimes we don't really need the trigonal. In the exam, it would accept if you simply put pyramidal. We've got another example where we can have 4 pairs of electrons. Remember, 4 pairs of electrons, it's based on the tetrahedral structure with a bond angle of 109.5. And now we can have an example where we've got 2 bonding pairs and 2 lone pairs. So I'm adding a lone pair. I'm basically taking one of these bonding pairs away and putting a lone pair in its place. And an example is water. Water is an example of a molecule with 2 bonding pairs and 2 lone pairs. And again, it's not easy to see on a 2-dimensional screen, but these lone pairs have arranged themselves in such a way so they're as far apart as possible. Lone pair repulsion is the greatest. Now, the inclusion of another lone pair, so basically I've replaced this bonding pair now with a lone pair, the result is it's forced these bonding pairs even closer together. And that reduces the bond angle even more. The bond angle now goes down by another 2.5 degrees and goes down to 104.5 degrees. So you can see the rule of thumb here is we've usually reduced the bond angle by around 2.5 degrees with the inclusion of a lone pair. Not always the case, but it's a decent rule of thumb. So the inclusion of this other lone pair has forced the bonding pairs even closer together. And we named the shape. Again, we're looking at the name of the shape here, made by the atoms, and that is also called a bent shape. Sometimes it's occasionally called V-shaped as well, but we'll just stick to bent. Now, we've looked at all the permutations where we've got 4 pairs of electrons. We've looked at when there's 4 bonding pairs, no lone pairs. That was my methane tetrahedral structure, and we've looked at these 2 examples. These 2 examples are very, very common, I would say. The example we looked at here with the CH2 is very rare, but these 2 are very, very common, so you do need to be aware of these. The next example, we've now got to move up to where we've got 5 pairs of electrons. And we're going to remember that if I've got 5 bonding pairs of electrons, that would give me a trigonal bipyramidal structure with bond angles of 120 and 90 degrees. I'm going to remove one of those bonding pairs now and add a lone pair in its place. So I'm going to have 4 bonding pairs and 1 lone pair. An example of this would be SF4. Now, if you remember our trigonal bipyramidal, I had 1 directly above, 1 directly below. I had 1 coming out towards me, 1 behind me. Now, in my trigonal bipyramidal structure, I would have had another bond coming here. That would be a trigonal bipyramidal, but I'm now going to remove this, and instead I'm going to add a lone pair in its place. And it's important that when we've got these shapes of molecules with 5 pairs of electrons, the inclusion of a lone pair will always be in one of the equatorial positions. I'm not going to go into the ins and outs of why, but it's to minimise the repulsion. There's a really good explanation on Chem Guide of why that's the case, but I'm not going to go over this here. But again, the reason is it minimises the repulsion. Now, the inclusion of this lone pair is going to reduce the bond angle here to, again, it's going to be below 120 degrees. Again, a sensible answer would be fine. I think it's, again, it reduced it by quite a bit. I think it's supposed to be around 105, but I think if you were to give a sensible answer below 120, you would get a mark for this. And the name of this shape is called a seesaw. And again, it's a lovely, if you actually draw the 3D, if you actually build a 3D model of this, it's really easy to see the seesaw shape. Now, if we to spin that molecule that way, so this lone pair was basically in the north position, it was here, you'd see that this is like my seesaw, and they're like my legs of the seesaw. We're going to move on now and look at the next example where we've got 5 pairs of electrons. So I've now got 5 pairs of electrons. I'm now going to introduce another lone pair. So I've now got 3 bonding pairs and 2 lone pairs. Again, this is quite a common one. An example here would be BRF3. And again, I'm going to remove a bonding pair from an equatorial position. So I've got my Br, I've got my 1 above, 1 below, and I'm now going to remove my 2 bonding pairs that were here. And again, we've got to remove my equatorial bonding pairs. And that there gives me the shape of a molecule if I've got 3 bonding pairs and 2 lone pairs. Now, remember that this bond angle here, if these were both bonding pairs, this bond angle here would be about 90 degrees. Now, the inclusion of these lone pairs means that this bond angle now is going to be below 90 degrees. And again, something around 85, 86, 87 would probably get you the mark in the exam. I don't think they're going to be too rigid on what that bond angle is, as long as it's a sensible answer below 90 degrees. And the name of this shape is, again, it's T. It's now called, it's a T shape. And again, that's quite easy to see because we've got the shape there of a T. You may think, well, you know, you could argue if you've got a shape like, I'll just call this A. If you've got a trigonal bipyramidal shape, you could argue that why couldn't these be in the lone pair position, and as such you would then have bond angle of, you know, maybe just less than 120. Now, this again is due to minimising the repulsion between the pairs of electrons. And again, I'm not going to go into the depth here. If you want to find out, you can have a look on Chem Guide, but it basically doesn't arrange itself in that way. Here you've got the lone pairs in the axial position. In reality, the lone pairs are always in the equatorial position. So it really will be T-shaped. If this was the shape, it would be just like a trigonal planar. But that's not the case. It should be T-shaped. Now I've got one more example where we've got 5 pairs of electrons. And that's where we've got 2 bonding pairs and 3 lone pairs. And that is when we've got an I- ion. And what we've got now is, if you have a look, I'm now going to remove another bonding pair and replace it with a lone pair. And again, it's got to be from the equatorial position. So I've got to remove that bonding pair and replace it with a lone pair. So that gives me 3 lone pairs in positions equatorial, and my 2 bonding pairs are in the axial position. As I said, this would be in an I3 minus ion. Here, again, we're looking at the bond angle between the bonding pairs, and I'm hoping we can see the bond angle here. The bond angle here is just 180 degrees, and as such, it is linear in shape. So that's where we've got 5 pairs of electrons, 2 bonding pairs and 3 lone pairs. 180 degrees linear. Please make sure that all these lone pairs are in the equatorial position. We're now going to have a look. We've done all my possible permutations where I've got 5 pairs of electrons around the central atom. So we're now going to move on to where we've got 6 pairs of electrons. And this is based again on an octahedral structure where my bond angles would be 90 degrees. But now I'm going to remove one of my bonding pairs and put a lone pair in its place. And this could happen in a molecule such as SF5. And let's just draw them. So I've got 1. I'm going to draw them above and below. And it doesn't really matter because all these are equivalent, so it doesn't matter where my lone pair is. And this is for an SF5 minus ion. Again, I'm not going to draw the square brackets and the minus, but this would be for an SF5 minus ion. And here we've got 5 bonding pairs and 1 lone pair. So I'll just make a note of that, 5 BP and 1 lone pair. And again, this bond angle here would be 90 degrees. But again, because we've got this lone pair in there, it's going to reduce the bond angles a little bit because lone pair bonding pair repulsion is greater than bonding pair, and this therefore is going to be less than 90 degrees. And again, a sensible answer, 87.5, 88 will be absolutely fine for this. The name of this shape, again, it's great if you've got a 3D model, you can see this quite easily. It's actually called a square pyramidal. So then the shape is a square pyramidal. So that's where we've got 6 pairs of electrons, 5 bonding pairs and 1 lone pair. The last one, again, there's lots of these, I know. The last one of these, if I've got 6 pairs of electrons, and this is where we've got 4 bonding pairs and 2 lone pairs. And an example of this would be XEF4, xenon tetrafluoride. And here, for the lone pairs to get as far apart as possible, if we think about our octahedral structure, the lone pairs are going to be here and here. They're going to try and be as far apart as possible. So you'd have lone pairs at 180 degrees to each other. And that therefore means that my bonding pairs would be here. And the bond angle here is 90 degrees. And the name of this shape is square planar. All these atoms are in the same plane, and this is called a square planar molecule. So they are all the shapes that you could be tested on. Some of them are more common than others. but in theory, the exam board could test you on any of these. What we'll look at in the next video is how we can look at the formula of a particular molecule and see if we can deduce the shape of that molecule based on its formula.